Okay, so we started talking about formal grammars. Then we talked about context-free grammars, and actually we looked at the whole Chomsky hierarchy: regular languages, context-free grammars, context-sensitive grammars, and the most general ones: type 0, type 1, type 2, type 3 grammars. Then we looked at grammar for English. Okay, English is a nice language to specify the language grammar as a context-free grammar because it is very order-dependent language. Okay, for languages like Turkish, where the order is not that important, word order is not that important. Well, word order is important, of course, but it is not important for the grammar. It is maybe important for the semantics. So we are not going to use context-free grammar kind of formalism. We are going to use dependency grammars, and we are going to look at those. We stop at this point 30. Okay, we said that okay, this kind of formalization is nice. Okay, this kind of verbalization is nice. I can explain many things in the language grammar, but many things are missing too. For example, subject-verb agreement. You don't say I reads, you say I read. You don't say she read, you say she reads, etc. So how are we gonna do that? How are we gonna do this? By achieving the subcategorization thing. Okay, like this. Come up with set of context-free grammars. One set works for the singular subjects and verb. The other one will work plural subject and verb, and etc. And if we can generalize this idea, we can do this generalization, subcategorization. Some words can be used. Okay, some words can be used with just a subject on the subject and verb. Some verbs need a PP preposition. Some verbs need a pronoun plus PP, and etc. Noun, phrase, and preposition, etc. See, these are the subcategorization stuff. So you don't have a single set of rules, many sets of rules, and each set is applicable to some of the words and nouns and etc. But we are going to ignore all of those because they look ugly. I know how to solve it, but I am not going to do that because it is not that elegant to express everything like that, and we don't need to because we know how to do that later when we are done with our whole grammar. Okay, so I'm going to ignore that part. Although not elegantly, I can deal with it. And there are many modifications, extensions of the context-free grammars like the L, FG, HP, SG, and etc. But as I said, I am not going to go into details of those. Okay, let's go back and let's talk about our tree banks. Like we did before, remember we had the Brown corpora for the part of speech tagging and other types of banks, data banks. Now we have the data bank for the parsing. We call them tree banks. Okay, so tree banks are these. Some people, they got together, very knowledgeable computational linguistic people. They get together and they chose a set of sentences and they produce trees for those sentences, and they said that this is the correct form of parsing a sentence like that. Okay, and let me give you some examples. For example, this is an example. Penn tree bank is a widely used tree bank. Also, Wall Street section of the Penn tree bank includes 1 million words from Wall Street Journal, and it is marked like this. Say that, okay, this is like a Lisp kind of syntax. This is the top node, These two are the children of it. Then there is one children and second children. This one is it says sentence has two parts, TPZ2 and comma, noun phrase subject, the second sentence, etc. This sentence is noun phrase and verb phrase. In the noun phrase, we have just we. In the verb phrase, we have, okay, MD would, MVP have, and after that, another sentence, and subject is none, and this one. Let's read what it says. We would have to wait until we have collected on those assets. He said. Dot. Okay, so there is a comma. So the sentence is we would have to wait until we have collected on those assets, he said. That's the sentence. This is how I parse it. Somebody sat, or two or three people sat down and they put together the trees like this, and it's a very old data set. It was done during 90s, I guess. And we have those. So what are we going to do with these? When we write our parsers, okay, to come up with the parse trees for a given sentence, we are going to compare our results against these kind of parsing trees. That's what we are going to do. Okay, tree bank grammars. So you need to have a grammar first, right? Then you need to have lots of sentences. You get the grammar, you get the sentence, and as a person knowledgeable in this area, I sit and mark them one by one. Okay, and it says that this tree bank has 4,500 different rules for VPs only, verb phrases only. The main reason is, well, the language is something complicated. The second thing is that they said that we are not going to use any recursive rules. All the rules will be like this: VP, VBD, PP, or this one, propositional, proposition. And I don't think that they have continued this more than 4 times. Because sometimes, if you continue this more than 4 times, it will not make much sense. So they did that. That's why the number of rules is so high. But as you remember, noun phrases and verb phrases are the ones that are the cause of the language complexity. So, even if I had used the recursive rules for the noun phrases and the verb phrases, I don't think that this number would have been less than 2,000. So 2,000 rules for the VPs, and we have the noun phrases, and we have the proposition phrases, and etc. Everything. Okay, so that's one tree bank. Okay, tree banks are like those. Okay, each sentence is marked by somebody. I showed you that too. Let me give you one definition. Heads in a tree. Okay, so what is a head in a tree? Choosing the head in a tree is something to. Let me show you what's a head in a tree, and we are going to talk about why we are using it. Okay. So this sentence is: workers dumped sacks into a bin. Okay, very simple sentence, and this is how I parse it. As start or sentence is noun phrase, verb phrase. Noun phrase is, I guess, plural nouns, and VP is VBD, noun phrase, and PP. VBD is dumped. You understand it, okay? So this rule says that my head will come from the verb side. Okay? This rule says that one NP is only NNS, and this one will come from there. This one will say, okay, I have 3 children, but my head will come from the VBD. This one says PP, okay, I have 2 children, but my head will come from the P side. So it's a fully deterministic rule set to get the head of a sentence, okay? So head of a sentence is dump here. But if you are trying to find the head of a noun phrase, it's going to be this one, Ben. Okay, so each rule says that I will define my head this way, and each rule has head in it. Okay, finding heads in tree bank trees is a task that arises frequently in many applications. Okay, especially in statistical parsing, and there is a very well defined set of rules to get the heads of a tree, any tree. Okay, so when we come to dependency parsing, we are going to go back and look at this again. So I gave you this definition, by the way, okay. All the morning flies from Denver to Tampa leaving before 10. Okay, the head of this rule is, okay, flights. Well, I guess you understand what that head is. Head is what that phrase is all about, what that rule is all about. This rule is all about this flights, okay? All the flights, all the morning flights from Denver to Tampa leaving before 10, I can replace, maybe we can look at this picture like this. I can replace this thing with this single word, flights. Okay, flights. All the morning flights from Denver to Tampa leaving before 10 is cancelled. I can replace this with flights. Flights are cancelled, right? So it's kind of representing the whole tree, this flight. And as I said, this rule says that my head will come from this one. This one says that my head will come from this one. Nominal says the head will come from this one says this one, etc. So each rule will specify which part is going to produce the head. Okay. So we are going to talk about it. Lastly, up to now we talked about constituency. Remember, this is 46. Let's go to, okay. Remember this idea of constituency, a group of words coming together to form a constituency. Noun phrase is a constituency, okay? Verb phrase is a constituency. That's why context-free grammars work. You will say that, okay, a sentence is composed of a verb phrase and noun phrase. This is a constituency and this is a constituency. There might be 10 words under it, 5 words under it. Total of 15 words for this sentence, which is another constituency, okay? This is the basic principle of context-free grammars. This is the basic principle of defining context-free grammar for a language. But when we come to dependency parsing, okay, dependency grammars, okay, we say that you don't have to form constituents. You don't have to say, this is the order, verb phrase comes first and noun phrase comes later. You don't have to do that, okay? You don't have to do that. Would you mind stopping playing with your cell phone? Yeah, I am talking to you. You see, does he have his earbuds? He doesn't hear me? No, not you. Okay, you are listening to me, right? So what are you looking at? Okay, don't tell me. Okay, so constituency is not the only way to define a grammar. There is this notion of dependency grammar. Okay, in this dependency grammar, again, we have parse trees, but those parse trees are not dependent on the word order. Okay, So you simply define links between the parts of a sentence. The link between the words represent dependency relations between pairs of words. Okay, so you would say, let me, okay, these are important too, but let me show you this. This sentence, they hid the letter on the shelf. What is the head for this whole sentence? They hid the letter on the shelf. It is this one, right? The head. They used to tell us, bu cümlenin yüklemi ne? They used to ask this, right? So you find the head of the sentence first. Head is the head of the sentence. I found it. Now I'm going to define relationships between the other parts of the sentence with this one. So there is a relationship between head and they. It is nominal subject. Okay? So head and they is related with this relationship, nominal subject. Okay? Nominal subject. And then this letter and head is related with this relationship, direct object. Okay? It is direct object. Let's look at these. Nominal subject, clausal subject, indirect object, object of preposition, then modified dependencies, temporal modifier, a positional modifier, determiner. Again, remember the number of rules that is defined for English. We said that there are thousands of them. You can increase this number, but these are some of them. Okay, let's look at those. So head is related to they and letter. This is nominal subject. This is direct object. Letter is related to the with a determiner relationship. Letter is related to shelf with the on relationship, then determiner and the. Okay. Doesn't matter where these are happening. Okay. Okay, this is my head. Head is related to they by subject. Head is related to letter by object. This is a determiner. Okay. This is an on relationship. Okay. And this one is a determiner. So my whole tree becomes like this. So I am specifying the relationships between them, dependencies between them. That's why it is called dependency grammars and dependency parsing. Okay? So remember what we did with the Turkish sentences. Doesn't matter how, in what order you are saying the sentence, it means something, but they are all grammatically acceptable. This one kind of says too. I mean, it says that, okay, word order might be important, but as a dependency grammar, I don't care. I am going to only tell you the dependencies between the elements of a sentence. That's called dependency parse, and that's called dependency grammar.
So, is there nothing important about hit on the root? You said the order is not important.
Well, I mean, for dependency grammar, order is not important, right? That doesn't mean that order is not important for that language. Remember when we say sentence is VP and NP, this is an imperative. Well, let me do it the right way. NP and VP. From NP, I can get I. From VP, I get reads. I mean, this is possible to have. It's possible to have I reads being parsed for this grammar, right? Which is not correct. But I'm saying that this is still useful. Why? Because if I subcategorize it, etc. So this kind of a context-free grammar ignores subject-verb agreement. Okay, it ignores it. This kind of grammar just ignores subject-verb agreement, but I find it still helpful to do this kind of a parsing. And this one ignores the word order rules of the grammar, but I still find it useful. Why? Because if I am going to do the machine translation, if I get the head of the sentence like this head, I know that when I translate this to other language, to Turkish, okay, saklamak will be the main thing of the target Turkish sentence. Okay, so It is better than doing nothing, right? As I said, context-free grammars doesn't work for Turkish much. Okay, dependency approach has a number of advantages over full phrase structure parsing. Deals well with free word order languages such as Turkish, where constituent structure is quite fluid. Turkish is a fluid language. Parsing is much faster than context-free grammars. It's very fast. And dependency structure often captures the syntactic relations needed by the later applications, such as information extraction, right? Find me a person with an age between 50 and 60, right? So I am looking for a person that I found it. And what's the modifier of the person? Age between 50 and 60, etc. Okay? So CFG-based approaches often extract the same information from trees anyway. So why don't I do it in a faster, more convenient way? Okay, I am going to skip this one because I have a separate chapter about how to do the dependency parsing. And that will be it for this chapter, okay? This chapter is about context-free grammars, specifying a language with the context-free grammars, and specifying your grammar and parsing it, and etc. We talk about the tree banks, and that will be it. So if there are no questions, I will start a new chapter. Okay. Now let's do how we can do parsing. Let's do how we can perform parsing, okay, with a context-free grammar. We are going to learn two types of parsing. One is a bottom-up parsing, the other one is top-down, okay? And I am going to give two examples, one for the bottom-up, one for the top-down. Algorithms, parsing algorithms. And then without talking ambiguity, there is no NLP, right? I am going to talk about ambiguity. Good. Okay, so we are going to use this technique of parsing to produce proper trees, okay? Assign proper trees to input strings, okay? By proper tree, we mean, okay, this is the meaning of the proper tree. All and only the elements of the input, okay? Tree that covers all and only the elements of the input, and it has an S at the top. So I am expecting something like this. Book that flight from Ankara, right? So sentence is verb phrase, noun phrase. Verb phrase is verb and book. Determiner noun, that flight from Ankara. So is this a proper tree? Yes, it is. Why? Because this tree covers all and only elements of the input. So I covered, okay, I covered all the elements of the sentence, all of them. There is no uncovered word, and it is not needing anything else. And at the top there is an S. It's a proper tree. It's a proper tree. But it doesn't mean that the system can select the correct tree from among all the possible trees. Because given a sentence, I can find more than one parsed tree. That means what? There is an ambiguity in there. Let me show you one ambiguous example. Let me show you one ambiguous example. Where is my ambiguous example? I am going to find the ambiguous example. I think we looked at this before, maybe. I shot an elephant in my pajamas. The second one is saying, too, okay, I shot an elephant in my pajamas. Translate this to Turkish and translate this to Turkish.
Pijamalarımı giyerken bir fil vurdum olabilir ya da
Which one is which? Pijamalarımla bir fil vurdum. Is that one or that one?
Oradaki yani ben pijamalarımı giyerken bir fil vurdum. Soldaki.
An elephant. Soldaki hangisi ya?
Ben söyleyebilir miyim hocam?
Sen söyle, tamam.
Benim pijamalarımı giyen bir fili vurdum birincisi.
Evet.
İkincisi de pijamalarımı giymişken bir fili vurdum.
So this is a nominal, okay, this is a noun phrase. An elephant in my pajamas. Pijamalarımı giymiş. Fili vurdum ya da o değil ya, o pijamasının üzerinde fil resmi varmış herhalde, öyle mi? On my pajamas mı derdi o zaman? Her neyse, anladınız. Pijamasını giymiş. Fil pijamasını giymiş, adam da onu vurmuş. Bu ama I shot an elephant in my pajamas. Verb phrase preposition. So this PP is part of this VP. Okay? So both trees are okay. Both trees are parsed nicely. They obey the grammar rules, but their meanings are very different. Proper parsing doesn't mean to pick the correct one. Okay? It's ambiguous. Proper parsing means that finding both of them. Proper parsing means that finding a tree, there should be an S at the top, right? There should be an S at the top. At the bottom, all of the words should be covered. No word should be should be uncovered, and there shouldn't be any empty locations for the grammar rules. Okay, that's what proper parsing is. Yes.
You said all the words will be there, and we said only the words. Why we said only? Maybe how can?
Well, I mean, you cannot say that. Okay, there is a rule as noun phrase, verb phrase, and PP. You cannot say I covered this noun phrase and verb phrase, but PP is not covered. Okay,
Maybe yes.
but you cannot have that. Okay,
Yes.
that's not a proper
I
tree.
have extra word.
What?
I cannot have an extra word. I mean,
You cannot have an extra word. No.
except in my pajamas, etc. That means this is already covered. Why we say only words?
There could be two cases. In the first case, okay, I shot an elephant, and there is, let's say, I read, okay, books. In this case, I did not cover this books. This is not a proper tree, okay?
Yes.
And in the other case is verb phrase is two parts, verb and prepositional phrase, okay? And I am not going to put anything under the PP. This is not a proper tree either, okay? Is this the first time you are talking in this? You are in the correct class, right? You are taking NLP, right? Yeah. Sometimes it happens. Why are you? Sometimes they realize that they are taking the wrong course when they take the final exam. It happened a lot. Okay. So we talked about this proper thing, and I don't know what I was thinking there. Okay. So we are going to do the parsing to produce those trees, and both of them will be produced. Okay. Or as many trees as required by the grammar. There could be more than 5, 6, 7, whatever. Okay. So the process of parsing is, given the sentence, produce proper trees. However, there may be, we don't know. Okay. So let's start with some basic methods of producing those trees. Well, basic meaning bad. You know this rule, right? I mean, we in computer science we always give you the bad, straightforward techniques first, and we say that these are bad, easy to implement but bad because they are too expensive to run, and then we give you better algorithms, and for most of the times it's going to be dynamic programming based examples. We use dynamic programming in the NLP world a lot because dynamic programming is very good for one-dimensional data, and sentences are mostly considered as one-dimensional data. Okay, so for now, this is how we are going to do the parsing. This is how we are going to do the parsing. Okay, we will have all the words already in some buffer. That means what? I have the complete sentence. I don't start parsing before seeing the whole sentence. Human linguistic system doesn't work that way, I guess. We start parsing before the sentence ends. And most of the time it works nicely, but sometimes it fails. Let me show you a few cases where that thing fails. Sometimes it is funny. Okay. Now, yeah. Read this one. What? That's not funny. Somebody dead. Did you get it?
Yes.
I mean, I am parsing it. What is to be used for the beach volleyball?
Not mutilated body.
Not the mutilated body, right? It is the beach to be used. So when I say mutilated body, I immediately assume that mutilated body will be the subject of the sentence, right?
Yes.
So I read it, I started parsing it, I made my decision. This is the noun phrase. Now I'm looking for the verb phrase of it to be used. Use is the verb phrase here, right? It's around it. So mutilated body will be used for Olympics beach volleyball, right? And this is just weird. I'm going to, yeah, this one is good. Scientists count whales from space. Okay, so I mean, when I read scientists count whales, okay, when I see scientists count, okay, scientists are counting something. What are they counting? They are counting whales from space, right? So they are doing this. How many whales in the space? That's what we assume, but they mean this actually. I mean, they use the space pictures or the satellite pictures to count the whales, etc. So we usually do this, and sometimes, most of the time, it is funny. It looks like it is only funny for Engin only. Your name is Engin, right? Okay. For the rest of it, this is serious stuff. They like it. They understand it the first time. Did you get this one? No heart. It is just cognitive issues.
Kalbi yok, sadece bilinçsel sorun.
No heart or cognitive issues, they mean. No heart or cognitive issues.
Yani kalp sorunu değil de bilişsel sorun.
Both of them are no. Both of them are no. Well, the doctor says that Trump doesn't have any heart or cognitive issues. Anladınız mı ya? Ya gülünsene ya, anlamıyorum ki ya. Öyle boş gülmeyin ama. Trump'ı muayene etmiş doktor, demiş ki no heart cognitive issues demiş. Gazetede böyle başlık atmış. Zaten öyle bir şey de yok. No heart or cognitive issues demek istiyor herif. Bu no'yu bunu hem buna hem buna uygulayacaksınız. Adam hiç başkana kalbi yok, kafasında problemler var der mi ya? Bunu da buraya koymuşlar. But Trump needs to reduce his cholesterol, lose weight. Tamam ya, anlatmadım sayın bunları. Öbür taraftan devam edeyim. So the human parsing doesn't work like this one. For the human parsing, we can immediately start parsing the sentence without reading the whole sentence first. Okay, this one is not going to work that way. Okay, I have the whole sentence in my buffer and I am starting parsing after that. And the input is in the part of speech tagged. I don't know the part of speech, and we don't worry about the morphological analysis, and all the words are known. So very serious, very constraining assumptions, but this is the best we can do at the beginning, right? Okay. I mean, I can parse the sentences with lots of unknown words, right? Unknown to me. I'm speaking in English. When I read something, okay, 10% of the words, especially very technical stuff from other areas, 10% of the words, I don't know what they are. Okay? And we don't worry about the morphological analysis. If I don't worry about morphological analysis, I lost half of Turkish, right? That's what happens. And I have all the words already in the some buffer. No. Usually I start parsing before hearing the last word of the sentence. These are all problematic in various ways and would have to be addressed in real applications. So let's start using this stupid technique of doing the top-down search. That's what we are going to do. Okay. So let's say I am trying to parse this sentence, book that flight. Well, translate this to Turkish. Uçuşu rezerve et. So it is imperative sentence. I'm going to parse this. So this is what I'm doing. If a sentence is going to be parsed, it has to be an S. But there are three possibilities for S. Either NPVP, okay, so this is like NPVP, I go to school kind of thing. This is an auxiliary NPVP, are you going to school? This is a question auxiliary. Then the imperative sentences, okay, read the book. So it could be this one, or this one. If it is this one, okay, if it is that one, then I can do, why don't I read this green stuff? Okay, I can do either, okay, as is C and PVP, right? I can decompose NP into that and num, or I can decompose NP into proper noun. In this case, I can do auxiliary NP, you understand it, right? Or in this case, I can do as VP, verb, noun, phrase, as VP, etc. So I am making this tree larger and larger, and I am hoping to produce at the end, okay, this one, a parsing as VP, verb, book, noun, phrase, determiner, noun, determiner that, and noun is flight, right? So this is my final parse tree. Okay, so every time I branch, and at the lower end or the lower leaf level of this tree, I hope to find a tree that covers all and only the words of the sentence, book that flight. This is called top-down parsing. It produces lots of unnecessary trees like that, but without looking at those trees, I cannot know if I am parsing this all right. Question for you. When do I stop this procedure, this going top-down? I continue this until I yeah, you find one proper parse tree, right? Should I stop at that point?
No.
No. Why?
I should go until 4 words. I should scan all 3 word alternatives.
Why? Yeah, but maybe there is an ambiguity, right? I mean, if you have ambiguity, you should continue making the search, okay, until you find all the possible parsings of the same sentence. But how do you know that how many different ambiguous meanings, different ambiguous parse trees there are for that one, it's going to be a problem. The other thing is this: there may not be any valid parses for the sentence book that flight, right? If it is not within the rules of the language, then, well, I cannot stop. I will go on and on and on. Because some of these rules are recursive. If they are recursive, then that's going to be bad. But maybe I can say, okay, so for each of them, I need at least one word, 1, 2, 3, right? I have 1, 2, 3. If I have for a new tree, if I have more than 3 leaves, okay, then maybe I should stop. I should not go on, because that's not going to be a proper tree anymore. Okay, that's called top-down space. As you see, it is not that efficient because you have to produce lots of stuff. Let's look at the bottom-up version. Bottom-up, of course, as the name implies, I should start from the bottom, from the words, and grow many trees upwards. Okay, like this one, book that flight. Okay, I am going to do this. Book, verb, that, determiner, and flight noun. But these are not the only things that I can have. For example, book is also a name, right? Book is also an adverb, etc. That could be something else. So I am going to choose the easy way here. I am going to continue with the correct decisions. Verb, determiner, noun, and verb, noun is nominal, determiner and noun is noun phrase, etc. And when you go up, I will go to this one. Okay, VP, and VP is S. Book that flight. So you are going upwards from starting from the words themselves. Again, I ignored what I could have with book or flight, or I ignored how come I didn't do this verb and determiner. Maybe there is a tree available to explain verb and determiner, etc. Okay, so this is called bottom-up search, and this is as inefficient as the top-down search. Okay, so top-down only searches for trees that can be answers or S's. Whatever top-down produces, it's always a tree, parse tree. Okay, but it considers many parse trees that is not consistent with the input words. Bottom-up always works with the words. Whatever it produces sub-trees, they are always consistent with the sub-sentence, but they may not come together, but suggest trees that make no sense globally. Okay? So both of them are inefficient. Both of them are exponentially expensive. So we are not going to choose anyone, okay, any of them. We are going to do something else based on dynamic programming, okay. And both of them, they need to stop at this point and go back and try other paths. That's what backtracking, okay. That approach is backtracking. You will say it doesn't work, so I have to go back and try something else. Okay. So the problem here is, even the best one, ambiguity again. How do you address the ambiguity? How do you know that you found all the properties? And the second one is, we keep solving the same problem over and over again. Why? Because maybe I invented this NP in many different trees, but I keep reinventing them over and over again. Okay, so this was the ambiguity part and shared subproblems. Okay, we don't want to redo the work we have already done. Okay, one example is this. A flight from Indianapolis to Houston on TWA. I know this is a propositional phrase, and proposition phrase. Okay, I know these three, and I need to use bottom-up or top-down parsing to solve these. But depending on where I am in my search tree, I will keep inventing these proposition phrase over and over again. Very inefficient stuff. Very inefficient stuff. That's why I need to find a solution to get rid of this problem. Okay, share some problems. Well, dynamic programming is very convenient to find a solution against the shared sub problem thing. Okay, any questions so far? Okay, if there are no questions, I think I will stop here. 10 minutes of break. After the break, we'll continue.
Anlamadım da. Hani bu top-down search'te diğerinde de vardı. Hani birden fazla hani büyük ihtimali var ya. Evet. Kaç tane olduğunu nasıl buldun?
Soru da o. Orayı ballandırdın.
Çok anlayamadım orada.
Nasıl bulacağımı söylemedim ben.
Ha.
Sen imza mı atacaktın? Unuttum ben vermeyi. Dersten kalırsan söyle bana. Hocam bir gün işe gidiyordum de.
Tamam.
Bence sen iş görüşmesine falan bırak ya. Sen derslerini de al. Tamam. Hafta içi ne stajı yaptırıyorlar ki sana?
haber verir misin abi? Okey. Hadi.
Şimdi vermedi. Ama şey dedi, yazmış olmadı yani. Çiğ.
Sana hesaplaması gerekiyor. Hesaplaması gerekiyor. Az bir şey.
Geliyor mu? Kendine gidelim. Acaba tarihini yeni dedi. Yanlış biliyorum. 2 tane var. Güncel. Sana denk geleyim. Yanlış verdim. Güncel yok. Vermemiş yani. Kafasını kaldırma.
O meyve şifalıymış hocam.
Efendim?
O meyve şifalıymış hocam.
Hurma mı?
Bodur palmiye meyvesi.
Bodur palmiye meyvesi. Ne şifası var?
Gerçekten hocam. Prostat büyümesine karşı.
İyi tamam. Nerede kim diyordu zehirli diye ya? Nerede Barış? Okay, so let's go back and let's try to. Okay, I'm going to skip this. We already talked about this, and we are going to do again using dynamic programming. We are going to solve this problem of finding all the ambiguous parsings of the same sentence. That's one thing, and we are going to do the avoid the repeated work. So don't repeat the same work. Solve the shared sub-problems once and produce all subtrees. Okay? And we are going to do this at the same time in polynomial time. Okay? Well, it is polynomial, but not exactly. But depending on how you look at the complex analysis, it's going to be polynomial. So we have two examples. One is CKY parsing. It's the initial letters of the inventors, designers of this algorithm, CKY. The second one is the early parsing. This one is bottom up. This one is top down. So I am going to look at the bottom up one first. Okay, CKY parsing is doing this. It says that for this parsing to work, and why we are doing this, it's going to be clear in a few minutes. All the rules, context-free grammar rules, will be binarized. Okay? First, we will limit our grammar to epsilon-free binary rules. So, all the rules will be like this: A, B, C, binary. We don't accept A, B, C, D, etc. Or okay, it could be like this. Either A, B, C, both of them are non-terminals, or A, a terminal. We don't accept anything else. You cannot write A, B, C, D, or A, alpha, B, and etc. These are not accepted. Okay, so what are we gonna do? We don't reject the grammar. We convert it, right? So we are going to convert any such rules to these kind of rules. It is not that difficult to write it actually. So this one is good. S, NP, VP is like A, B, C, right? This one is good. This is a terminal, but this one is not good. As auxiliary, noun, phrase, and verb phrase. So what are we gonna do? We are going to do this. Maybe we can convert it to such a case as x1 as x1 VP and x1 is auxiliary NP. So I made up a new non-terminal symbol x1, and using that now I am satisfying this binary rule thing. So playing these kind of tricks is the solution. Okay, is the solution. That's what we're going to do. The reason why we prefer our rules like this is because I am going to use this mechanism. I am going to say that, okay, from the word number I, from the word number I to word number J, I can explain this part of the sentence using this rule BC, ABC. And K is the border between B and C. B is from I to K, okay, C is from K to J. If I can do this, I to K is B and K to J is C, then I can put them together to produce an A. A is going to be from I to J. And recursively continuing this, I am hoping to reach to the top level S, which explains the whole sentence. That's what I am going to do. Okay? So if A spans from I to J, then there must be some K such that B splits from C someplace and K is the border point. So K is between I and J. So all the rules are like this. How about this rule then? How about this rule? Well, this rule is already a single rule. I know the word number. I know if it fits or not. And that's a simple thing. Okay, that's called CKY parsing. And if we use such rules, and there is this parsing strategy, it specifies a way to find all possible parse sentences, parse trees. Also, it's going to eliminate any repetition of the same work. Okay. What if your grammar is not binary? So I'm going to show you a way to do it. Okay. Convert to a binary. It is called, by the way, it's called Chomsky normal form, CNF. Okay. CNF. Okay. So the resulting grammar accepts the same set of strings, but the grammar is different. So I am modifying, I am augmenting the grammar a little bit. I am modifying it. It accepts the same set of strings. It rejects the same set of strings. But the trees are a little bit different than the original grammar. But that's okay. Okay, so this is what I'm going to do. A, B, C, or A, W. Non-terminal, non-terminal, non-terminal, terminal. So if you have such a thing, okay, you will do this. If you have such a thing, so you will do this. Okay. Good. And if you have this one, A, C, then you know that at some place C has to go to terminals, then I can replace it with this one. So you are modifying, you are changing your grammar a little bit so that you do Chomsky normal form automatically. Okay. So binarization, intuition, I already talked about. Yeah. Okay, let's look at this one. This is a grammar. Let me raise this. My grammar is this. Very simple grammar. Remember our L1 grammar, as after L1 there is an no, you didn't see this yet. You saw L0 but not L1. So a sentence is noun phrase verb phrase. Okay? Or a sentence is auxiliary noun phrase verb phrase. Or a sentence is a verb phrase. Okay? So which rules are okay with us in terms of Chomsky normal form binarization? This is okay. This is fine, right? This is fine. This is not good. Not good. Not good. Not good. This is fine. This is not good. Okay. Let's mark the ones that are good. Nominal noun. This is okay. This is okay. Okay. Okay. Okay. Okay. How about this part? These are all okay, right? Because all of them are terminals. These are all okay.
Nominal noun is not okay, I think so. Because
Which one?
noun is terminal.
Which one?
Nominal noun.
Nominal noun is not okay, yeah.
The one below that.
Nominal.
Nominal noun. Yes.
Oh, there is a. Okay, I thought. No. I thought this is this is a recursive rule. This is one non-terminal. This is another non-terminal. Yeah. So this is, it's like, there is no nominal PP. There is nominal and PP. Nominal is this.
Noun is terminal.
Noun is not terminal. Noun is either book or flight or meal or money. Noun is not terminal. Okay? So I'm going to convert it to a Chomsky normal form. How am I going to do that? Let's do this. I think we did that already, this one. S is x1 VP and x1 is NP auxiliary NP. Okay. How about this one? How am I going to do that? SVP, VP is verb, right? And verb is this one. So I'm going to change it to as, tell me what? What? As, yes, as book or include or prefer, right? Because as VP verb and it goes that way. This is okay, this is not okay, I'm going to change it. You know how to change it. And this one is NP pronoun and pronoun, so I'm going to make it NP goes to I, she, me, right? It's like that. So I can change this one. Do I have it? Yeah, okay. Like I did. NP has changed. So it's partially done. It's not the exact same thing, but it's partially done. Any questions? Okay, so let's look at this CKY parsing, how it works. So let's build a table so that an A spanning from I to J in the input is placed in the cell IJ. So I will have a table, okay, indexed by I and J. Okay, so I am going to put an A if A explains the words between I and J, and at the end I am expecting NS in the cell 0N. 0N means N is the last word in my sentence. 0 is the beginning of the sentence, and I am hoping to see an S at that position. So I'm going to build a table bottom up. We will know that the parts of A must go from IK to, because A should be I to K to J, and if A is something like this, then in the box IK there should be a B, in the box KJ there should be a C. Then in that case I can put A to box I to J. Okay, that's what I'm going to do. So it's going to be something like this. So this is the table, the position 0, 1, 2, 3. Okay, here I have the box for 0, 1. Between 0 and 1 I have this book. This is 0, 1. This is 1, 2. This is 2, 3. Let me write the names in there. This is 0, 1. This is 1, 2. And this is 2, 3. So bottom up approach. What can I write for the 0, 1? Why don't I? Let me erase these. What can I write in 0, 1? Book, right? Let's go there. Book is verb phrase, right? I can write VP there, right? Book is verb phrase. What else? Do you see book? Okay. Book is a sentence, see? Book is a sentence too. Okay. So I found the letter S, I found the non-terminal S in my table somewhere. Doesn't mean that this is a proper parse tree. Why? Because this S only explains this one, book. How about the flight? Those words are not covered. So this is not good, right? This is not good. So, but it's okay now. So what else I'm going to do? Can I write something else in that place? Other than that, book is a verb phrase.
Nominal.
Is that a nominal too? Yeah, nominal. Yeah. Let's write Why don't I bring this to this space and make it like that? Now I can do it right. Okay, so nominal. Okay, what else? That's it. VPS and nominal. I can do that. Okay, so we fill this table like going this way and one by one and going upwards. Okay, so I am done with the first column. That's all I can do with the book, the word book. How about this column now? I start from this one. 1 to 2, it is the. Where do you guys see the? Where is the? Do you see it? I think I did not copy everything from the other thing. It is missing, right? This determiner thing, determiner the. right?
Yes.
So maybe I should add this one. They didn't have enough space to add this one. Determiner the, and I am going to add determiner here. What else? Nothing. So I cannot do anything out of this word the. Okay. So let's look at this place. What is this? This is 0, 1. This is 1, 2, and this is what? You tell me. This is 0, 1. This is 1, 2. Column number 0, column number 1, column number 2, etc. Row number 1, row number 2, row, okay. So this is what? 0, 2. Okay. This is 0, 2. What does it mean? What can I make out of this 0, 2, 2? Book the. So what am I going to do? I am going to, so my I is 0, my J is 2. If I make K1, okay, if I make K1, can I find a rule such that A, B, C, this is 0 and 2, K is 1, okay. Between 0 and 1 there is B, between 1 and 2 there is 2. So can I find something like VP determiner? Do you find it? Do you see it on the right? VP determiner? No. That would be like not that meaningless, right? VP determiner, no. How about S determiner? Do you see it? S determiner? No. Nominal determiner? No. Unfortunately, I can't put anything in there, right? I can't put anything in there. So this space will be empty. Okay, good. Let's move on. Okay, how about this one? Are there any rules like this one? A determiner. If there is a rule if there is such a rule, then I can put A in there too, right? But since we are in CNF binary form, this cannot happen, right? This cannot happen. If it happens, it's going to be either the on the right as a single terminal, or it has to be A, B, C thing. So let me erase this. It cannot happen. Okay, let's go to here. 2, 3. We have 2, 3. What do we have in 2, 3? Flight. What is flight? Flight is a nominal. Right here is a nominal. Flight is a nominal. And what else? Flight is, that's it? Only nominal? Flight is only nominal. Yeah, it's a noun, right? Yeah, flight is only nominal. That's good. Good. Originally, I think there was nouns. There was noun. There. Okay, where is it? Now, yeah, see, noun, book, flight, meal, money. Where did the noun go? Where did the noun go? See this one?
Instead of noun.
Yeah. See this one? We don't like this kind of a rule. We cannot say both left side and right side is a single non-terminal. We have to convert all these nouns, get rid of nouns, and we said nominal book, nominal flight, nominal meal, nominal money, right? We did that. That's why it's gone. Okay, good. How about this part? What is this? This is, you tell me. No. Tell me what is inside the green stuff. What comma what?
1, 3.
1,
3.
3. Yeah, 1, 3. This is 1 and 3. So I am trying to make sense of the flight. So I is 1, J is 3, K is 2, right? From 1 to 2, the 2 to 3 flight. Okay. From 1 to 2, I have determiner that. From 2 to 3, there is nominal. Are there any rules that says determiner nominal? Do you see it?
Yes, NP. Determinal nominal.
Which one? Yeah, this one NP. Okay, this one is NP, right? Rule NP, it says determiner nominal. What else? Do we have anything like that? I guess no, right? No. Determiner nominal. Good. Okay. See, that's the rule. First column, second column, and third column. It looks like this is an upper triangle matrix. We are not going to fill in those parts. Okay, because they don't make sense. They are like okay, this is 0, 1, this is 0, 2, this is 2, 0. 2, 0 is just the inverse of the letters. No, it doesn't work. So let's look at this one. This one is important. This is trying to make sense of all the words 0, 3, right? 0, 3. How do I make 0, 3? In this case, I is 0, J is 3, K could be 1 or 2, right? If K is 1, let's do that. Erase this part. So I, J, K, 0, 3. If K is 1, it means what? Look at 0, 1. 0, 1 is this. Then look at 1, 3. 1, 3 is this. So, do I have any rules on the right that says nominal NP? Do I have any nominal NPs anywhere? Nominal NPs? No. Nominal noun, nominal NP. Well, it doesn't work. Nominal NP doesn't work. Okay. So nominal NP did not work. How about SNP? Do I have any SNPs on the right? No. How about VPNP? Do I have any VPNPs? Yes, there is one. Okay, there is one. So I found it too. And it looks like I can't find anything else. So I am done. I am done. So happy ending. At the end, I found an S in this box 03, and it explains that I can assign an S to this one. It looks like these are my arrows. Let me draw my arrows in black. Okay, VP, NP, and this NP is NP nominal. That's my tree. That's my tree.
Do we not check for k equals 2?
What?
Do we not check for k 2?
Yes.
Oh yeah, well we should do that too. Yeah, well, that's a very well. Thank you for reminding us. 0, 3, K2. Let's look at 0, 2. What is 0, 2? Inside 0, 2, unfortunately, I don't have anything. Since I don't have anything, I can't combine this with 2, 3, which is this one, right? I have to combine these two. That's why. Well, it doesn't produce anything, but I have to check it anyway. So I have to
Sir,
check.
I think we should also note the K value to backtrace.
Well, I don't have to because I had drawn this one. I mean, if I had any connection, I would have drawn. That there was a arrow between this one and that one. Arrows are good enough, but K is a good idea too. Yeah. For each of them, I can say like K is 1, 2, etc. Good. So this is called C. Okay. CKY parsing. CKY parsing. And it requires your grammar to be in Chomsky normal form. Okay, Chomsky normal form. And the reason why we need the Chomsky normal form is this. Okay, I need to. If I like to put a non-terminal in a box, I need to find the rule that explains that letter by combining one box with another one, So I am iterating over all the K values from I to J, and testing each one by one. If I had rules like A, B, C, D, A goes to B, C, D, then I had to have K and L as two indexes. That was going to be complicated, so I don't need that. I am doing it this way. Okay, cool. So this is the CKY parsing. And this is how it works. Let's look at, okay, this is the algorithm here. Algorithm is this. CKY parse, give me the words, give me the grammar, I am going to return you the table. For J, is I am going to start from 1 to length of words, 1 to n, okay. First initialize it. Tell me what this one says. Table J minus 1J. At the beginning it is 0, 1. Remember what it did here? It is, this one is 0, 1, right? This is 0, 1. In position 0, 1, J is 1, right? In position 0, 1, put all the non-terminals that go to a word in J position J. Remember at the beginning, position J, position 1, there was only one word, book. There can be at most one word, or there can be exactly one word. Book, and book is explained by nominal, I guess, or what was it? Book was explained by nominal, yeah. Okay, book was explained by nominal. Also, book was explained by a sentence and a verb phrase. Okay, so at the beginning I did that. I placed something in here. Then I am going to, okay, this is what I did. Then I am going to go into this loop. I from J minus 2 to 0. So what does it do? J minus 2 to 0. What is J at the beginning? It is 1. Okay. J minus 1, 2 is, minus 1 doesn't work in this case, so I'm going to skip. I will do this, and I'm not going to do anything for this loop. But when J is, okay, this is J, right? J is this way. It will start from 1, then J2, then 3. So this is J1, 2, and 3. Okay, when J is 2, I initialize it, this box. Then I am going to fill this one in. Okay, let's look at the general case. When J is something bigger than 1, 2, 3, from J minus 2 to down to 0, then I am starting doing this K thing. Okay. For this box to fill in, I will try to add these two. Do they make any rule? Okay. If yes, then I'm going to put it in there. Then I am going to do this. So in this case, K is 1, K is 2. Just two places I checked. Okay. And continue this until all of your loops are done. All of your loops are done. When you continue on this, all of your loops are done. And that will give you the complexity of the thing too. What is the complexity of this algorithm? Something like a cube, right? This is n, number of words. This is n, number of words. N. How about this one? This is I. Again, this is number of words too, right? From n. And this one is number of words too. N. How about this one? This one says that check all the rows in your table. So this is like checking all the rows in your table. This is like number of rows. Let's say it is m, right? So it is like n cubed times m. N is not bad, right? N is like, let's say 20 words. N to the 3 is not that bad. If m is 4,000, something like that, it's going to be expensive if I'm going to scan it. But I think I can look it up using some kind of a hash coding or similar technique in O1 time. So we are talking about something like O n to the 3. Okay, polynomial time, expensive polynomial time, but still in polynomial time. Okay, good. Another example for dynamic programming. Okay, filling in a table. I think this is the third time we are filling a table. Right, the first time is the edit distance. Second time is the part of speech tagging. Now we are doing the CKY. Okay, yeah, this one is an example from the book. Let me get rid of this one. Book the flight through Houston. Okay, let's look at this one. Book could be SVP verb nominal noun. How come we miss that verb and noun thing? Did we miss it? Maybe it has a different. Where is verb thing?
Table was incomplete.
I think the grammar was not complete and we missed it. Where is verb? Yeah, verb is missing, right? All the verbs lead to something. Yeah, verb phrase. Yeah, I think these are the rules that are changed or affected. They did not list this part. Verb, yeah. Noun, verb and noun is there, right? They are not changed. So I have to add all of them there. So for the book, it is SVP verb, nominal and noun. And we shouldn't be happy that I found an S in there because, again, this explains only one word, but the flight through Houston is not explained. Then let's look at this. Okay, how are we going to do it? We are going to do it like this. Go from left to right. J is incremented one by one. And then what was the second index? I is decremented from J minus 2 down to 0. So this is J is incremented one by one and I is decremented one by one. So I did that. Then I am going to do the second one. 1 to 2 is there is determiner. I couldn't find anything in there. How about this one? Flight is noun and nominal. Okay. This place is determiner, noun is NP. Determiner noun is NP. So let me mark it. Determiner and noun is an NP. Okay. How about this position? What is S in there? Book the flight. I think it is VP and NP, right? How about VP? How does the VP happens? How does the VP happens? VP happens by VP, NP. What are the rules for VP? Verb, NP. Yeah, verb, NP maybe. Let's go to the rules. VP happens, verb, NP once, okay. Verb, NP. Okay, that's the verb, NP. Let's go there. Verb and NP. How about X2? What is X2? X2 is the new non-terminal that we made up to make our grammar into a Chomsky normal form. Okay, let's go to X2 definition. X2, where is it? Where is it? Okay. Well, this grammar is not complete. It did not give me the X2 thing. I think X2 is about nouns and that kind of stuff. What?
It's a verb and P for X2.
Where is X2? Did you say X2?
Yeah.
Where is X2? This is X2. Oh, okay. Verb and P is here. Yeah. So what is it? This verb and P is an X2. Also verb NPs and VP, yeah, they are leading to the same thing. Yeah. It's not complete, but it is more complete than we thought. Okay, the same thing. It is verb NP is X2 and NP this. Okay. That's the whole thing. Let's go to this one. 3-4 is preposition. 2-4, to calculate 2-4, I need to combine noun with preposition, nominal with preposition. You won't find anything. How about this one? To calculate this one, determiner with empty, right? Or noun phrase prepositional. Noun phrase preposition, it's empty. Did not work. And how about this one? How about this one? It is this one and this one, right? 1, 2, and 2, 4. It's empty. 2, 4, and 2, 0, 2, and 0, 2, and 0, 2, and this one is 2, 4, right? Okay, this one is that. How about this one? This one is 1, 4. It is 1, 2, and 2, 4. Or 1, 3, and 3, 4. Nothing happens. NP prep doesn't work. So how about this one? 0, 4, 0, 1, 1, 4. It's empty. 0, 2, 2, 4. Empty. How about this one? Does it work? As prep doesn't work. As prep doesn't. VP prep doesn't work. Empty. Okay. And going this way, let's look at this one. So for this one, 0, 1, okay, 0, 1, 1, 5. Does that work? VP and P, it works, right?
Sentence, yes.
Yeah, so maybe this S is there, right? So let me erase all of this stuff I'm going to use. I'm erasing this. I am going to do this. So it is VP and NP. Right, it works. So that one works. What else? What else?
NP is a VP.
What?
Verb NP.
Verb, which one? What are you talking about again? VP and P works, right? Verb and P works too? Do we have such a thing?
VP.
Verb and P?
Verb NP is a VP.
I don't know. I mean, it could be, but how am I gonna draw it? Verb and, okay, this one. Like another S, verb and P.
No, we're talking about VP. Verb phrase for verb and then
We already did that, okay? Verb phrase, noun phrase, we already did that, right? How about verb and P, Engin says? Verb and P. Do we have verb and P? Verb and, yeah.
Yes, VP is verb NP.
Well, we don't have VP and P, right? We don't have, do we have VP and P?
VP NP sentence, I think.
Yeah. Verb MP is a sentence too. This is MP, VP. Where is VP MP? We don't have it?
SV.
Yeah, verb, yeah, no. We don't have VP MP. It's just verb MP. So I marked it wrong at the beginning. It is verb and MP, right? How about this one? 0, 2, okay. 0, 2, and 2, 5. This one is empty, not work. 0, 3, and 3, 5. No, it is not 3, 5, it's not empty, it's PP. VP, PP, right? VP, PP works. I think VP, PP works. This one is PP and VPS. Find the grammar. VP, yeah, VP, PP works here. So what does that mean? It means that our sentence is parsed in an ambiguous way. There are two S's. One is this. Book the flight to Houston. The other one is book the flight to Houston. Well, they are the same thing. Somebody translate this to Turkish. What kind of question is this? Somebody translate this red thing into Turkish and somebody translate this green thing into Turkish. Red thing. I don't know what kind of question is this, but you understand the question, right? Somebody translate this red thing into Turkish and somebody green thing. Then after that we are going to take a break. Book the flight to Houston verb. The flight to Houston is the noun phrase, right? For the red one. What is the Turkish phrase for flight to Houston?
Üstünden geçen uçuş.
Üstünden geçen uçuşu rezerve et, değil mi? Üstünden geçen uçuşu rezerve et is the translation for the red thing. How about the green thing? Book the flight through Houston. Through Houston is the prepositional phrase.
One says the flight is through Houston, the other says
Book through Houston.
booking Houston.
Yeah, so what is the Turkish sentence? Houston'u ara, bana yer ayırsınlar. Huh? Something like that. Houston üzerinden Houston'dan uçuşu ayırt. Well, I think that we have the same ambiguity in Turkish too. Houston'dan uçuşu ayır. Houston üzerinden uçuşu ayır. I think it is the same thing. The same ambiguity exists in Turkish too. Anybody knows Arabic? Maybe it is not. Anybody knows anything other than Turkish or English? What language?
German, but intermediate.
So translate this into Turkish, German.
German is also
Does it? Are they different?
As I know, German is same as English.
Yeah, they are the same. Yeah, they are preposition phrases and everything. Yeah, but sometimes there are some common phrases used for these kind of cases to disambiguate stuff. It's not the grammar all the time, right? Sometimes it is the phrases that you use. Anyways, so what? Ask this to Google how it translates to Turkish. Maybe you can ask this, through Houston, book the flight. Book the flight, comma, through Houston.
Şey diyor hocam, Houston üzerinden uçuş rezervasyonu yap.
Araya bir virgül atsana. Book the flight, comma, through Houston.
Book'tan sonra mı?
Book the flight, virgül, through Houston.
Değişmedi hocam.
Türkçesi de aynı çünkü. Türkçesi de ambiguous.
Houston üzerinden uçuş rezervasyonu yap.
Same thing. Almanca için yapın onu. Araya bir tane virgül koyup.
Almanca mı çeviriyor?
Evet. Yani farklı cümle veriyorum, ona bakalım. Book the flight through Houston and book the flight, comma, through Houston.
Wohin Sie denn nach über Houston?
Try the other one.
Same as English.
Same. I don't know. Maybe it's not as sophisticated as that we think the Google Translate. Anyway, so what I achieved here, okay, this is good, right? Book the flight through Houston, VP and NP. The flight through Houston is the NP, right? So that's the meaning. The other one is book the flight through Houston is, okay? It is booked through Houston. Good, so we prevented any repetition. I discovered this MP only once and I didn't have to work. I said that from word 1 to 5 there is an MP and I kept using it all the time. And I can put more than one S's into the same box and that's going to give me ambiguous ambiguous parsings of the same part of the sentence. Good. So we achieved whatever we wanted. Happy ending. N to the power 3 times some constant, the complexity, and that will be it. It will work for the grammar specified in BNF. Good. Any questions? Okay, no questions, then let's take some break. Then we will come back and we will finish up with the chapter using our anyway, okay, we are going to come back.
May I submit some things?
Nasıl atmadın ki senin imzanı?
Biraz geç geldim.
Tamam, çabuk. Arkadan cam açabilir miyiz arkadaşlar? Telefonum için bilir nerede unuttum ben. Yukarıda unuttum demek ya.
Geçen yıldan falan mı?
Yok.
Yine yanlış yaptım.
Benim için de beğendim de. İşte falan.
Diğerlerine göre
Ama galiba şöyle bir şey daha buldum. Ben bu internetten başka bir fotoğraf falan buldum. Bunu koydum. Ama sonra şey buldum. Şöyle bir şey var. Bizim sitede aynen kalmaz da onun üstünde her şey
onlar kendi zamanı.
yani aslında süreyi ama ben şimdi ben böyle olduğunu düşünmüyorum. Ben en yapmam
Yok. Telefon son seni çekiyor. Şimdi ben telefonu konuşmam.
Osman Hoca'ya konuştuğum şey bu. Müsait bir zamanda projeyle falan çoğaltmışlar. Ben kendim için getirdim de seninkini istemiştim.
Neler yapacağım?
Tabii tabii çoğaltacağım. Aynen.
Ben görüyorum. Yani ben de nasıl yapacağım alakalı yapılmış çalışmalarla ilgili bir şey istemem. Herhalde olay sayısının inceleyip hata sahneyi.
Ama seninki yolda.
Ya ben de sanatçıları şey yapmışlar, basın sesini veya sıcaklık ortamı özelliğini çıkarmışlar. Onun sonucu oluşan fazla çıkarken o uygulamayı kabul edecek mi?
Mesela bir tane şey yanlışlıkla yazdım.
Hiçbir şey yapmıyor. Adamın insanlarımızı olan değil. O her şey keşke yapsın ya sürekli. Ya şey yapsınlar da şöyle sonucu yapmıyor mu? Ben biraz ilerledim. Uygulamam benimki böyle. Webcam'den sen biliyorsun değil mi? Webcam işte o video streamini. Bir an şeyden program yapmış. Kamerasına eriştim. Birazcık bekleyince bir şeyler yaptım. Kamera koydum. Öyle o kadar. Şu anda işte beklenten falan var. Ben bir şey yapmadım da ben bir zaman. Şimdi baştan kazanmıyor. Hocadan o beyaz kalmıyor. Hani öldüğüm kırmızı. Person identification. Yani insana vücut tanımı.
Kanun olarak galiba. Hocam.
Aa, ciddi misin? Arayı nereden bulacaksın? Bulsana yani. Arı sokağına kadar korkarım. Arkadaşlar yapıyoruz.
Çarşamba sınavı var.
Çarşamba ne? Direkt başlıyorsun. Anladın mı? Hakan sana bırakmıyorsun yine.
15'ine bir de 30'una. Evet, 45'te geçtim. Ben de 45'te. Herhalde bitiyor dedim. O yüzden. Evet.
Bizim böyle kolay değil ya. Hiç değil, güç gibi.
Evet.
Asla kolay
Yarışından galiba geçen yıl kolaymış. Bu yıl da başladı.
Ya bizim şansımıza tükürsün.
Ağır dersin.
Her sene böyle aynı
Alıyor
şey.
musunuz? Ağır dersin.
Arıyor mu yok ben anlamıyorum.
Onları sadece geçen yıl bir tane şey vermiş. Benim yine aynı yapar herhalde. Şimdi de şöyle oldu mesela.
Şöyle oldu.
Aynen. Ve sonuç ödevi yapacak. Evet. İşte o günlerde de geçen yıl sadece onu yapalım geçirmiş.
Çok komikler ya.
Ben de böyle yapıp geçirdim ama öyle olmuş.
Bir şeyler diyorum ya. Her şey şanslı. Benim üzerim kitaplarımda dersin ödevi falan sormuştum. O kadar kolay ki. Bizim ülkede bile değil.
Şeyden o muhabbetten ben çıktım.
Ciddisin. Başından beri bana bir kanunlar söyledi.
En son Cem Ozan'la bir tane konuşuyoruz. İşte ikisi söyledi galiba bize. Böyle olabilir falan diye. Ya öyle mi?
Oradan
Yaptık böyle. Aynen.
dedikodu böyle yayılıyor
Evet,
işte.
dedikodu işte. İşte öyle bir yerde tekrar bize geldi. Ben de inanmaya başladım.
Acaba gerçekten sadece sizden mi yayıldı?
İşte onu bilmiyorum. İnşallah sadece bizden yanılmamıştır da. Gerçekten de.
Aynen.
Kaynak ben.
Aynen.
Bence yok. Güzel sistem de iyi olmuşsun. Bence sıcak.
Eğer konuda da çok basitmiş.
Ya basit değil, yaşın adamı genel sevmiyorum.
Ha, evet, o.
Hiç sevmiyorum.
Şimdi çok tamam.
Benim sınıfta şey yapmışlar. Benim sınıf proje yapmışlar. Böyle
Güzel sadece sensin.
Eski teknoloji bölümünde
Kırırsın sonuçta şey.
fabrika
çalışanlar da var. Yani sen şanslısın. O zaman arabada falan gider.
Alo. Çıktın mı sen dersten?
Tamam. Yok, çıkımda bir ders daha var. Görüşürüz ondan sonra. Ben seni aradım da göremedim. Olabilir. Bir arada baktım, orada göremedim. Buradan zaten bildim. Yani denk gelmedi. Sonra görüşürüz. Hadi kendine iyi bak.
Okay, so this is how bottom-up parsing works. You definitely start from the bottom and you try to make sense out of these words, and you hope that at the top there is an S symbol connecting available already parsed stuff. We are not missing anything. We are recovering, we are parsing, we are assigning all possible rules to all possible consecutive words. So we are not gaining this efficiency at the cost of some accuracy. It's all accurate, it is all done, it is exhaustive. Okay, so we did that already. Okay. I guess this is doing, yeah, oh, there is a third one too. What is this? Yeah, there is a third one. The book says that, okay, there is a third one, S1, S2, and S3. It looks like it comes from this X2 thing, okay? VP X2, right? It is coming from the same box, so its meaning is the same. Remember, we modified our grammar a little bit. Because of that modification, we are filing the same rule 2 times. It is X2 PP and VP PP, and X2 is already some kind of a VP, so the meaning doesn't change much. Okay, good. So 3 of them, and we can do it that way. Okay, since it is bottom up, CKY populates the table with a lot of phantom constituents. What do I mean by phantom? It means this. I am only using, okay, this PP, which uses this 2, and this VP, which uses, this VP uses what? This VP uses noun and NP, right? This one. So 1, 2, 3, 4 boxes only used. Okay, this one, okay, this S thing, this nominal thing, they are all ignored. So I am producing lots of phantom constituents that will never be used for anything. But without producing them, I cannot know that they are not useful. I have to produce them first. But at least I am not producing them more than once. I produce them only once, and I reuse them for many different uses. Okay. So some people say that, why don't we choose our direction in the other way, top-down way, not the bottom-up, but top-down. Okay, top-down way. That way I can avoid producing these kind of phantom constituents. Well, that's not going to solve the whole problem, but at least we would try it. For that one, we have this early parsing. Okay, Early parsing doesn't need to convert our context-free grammar to some other case. It allows any arbitrary context-free grammars, including the binary rules or the ternary rules and etc. And it is table-based. Our table is length n plus 1, like remember we have n by n table for the CKY. For this one we have a table of length n plus 1. So it's not a matrix, just a table, one-dimensional table. N is the number of words. And inside the table entries, we have rules like this, modified rules. This one says that here I am expecting an S non-terminal. This one says that at this position I have seen an S. This one says that, okay, I have seen an MP at this position. I am expecting an VP. I am trying to complete this S rule, okay? So simple modification to the rules. So there is a dot. Dot is the current position. So at the beginning, I am definitely waiting for this dot S, okay? At the beginning, I am waiting for dot S. I am waiting for this dot S, and I am going to show you how it is done. So table entries will be completed constituents like this, in progress constituents like this, predicted constituents like this. Okay, one of the trees will be there. So this is VP is predicted. This one, and NP is in progress. I have seen determiner. I am expecting a nominal. This one say that at this position I have seen a VP which was composed of V and P. Okay, these are the dotted rules. But rules are exactly the same, but in our tables I am going to insert the rules like with a dot. Okay, so this one I am at the beginning 0 0. I am predicting a VP. This one says that I have seen a determiner from 1 to 2. I am predicting a nominal. This one says that I had seen a 0 3 a VP, which is composed of V and MP. Okay, good. So let's see what kind of come on. Let's see in action, this rule in action. Okay. Let me show you the algorithm itself is not complicated, but if I show you the algorithm itself, it will be easier to understand. Then after that, we are going to come back and see what kind of things this incomplete predictor and scanner means. Okay, so this will be our table. Book that flight. So I have a table. Book that flight is 3-word sentence. I have a table of size 4, C0, C1, and C2, and C3. First, when you start, okay, inside C0, you are predicting everything, okay? You are predicting everything. I am predicting an S, okay? Chart 0 is this, okay? I am predicting an S. Since I am predicting an S, I am predicting this one too. Dot and PVP. Also, I am predicting this one. I am predicting this one too. Since I am predicting an NP here, I am predicting a pronoun and this one. See, I am predicting everything in chart 0, including all the dictionary stuff, okay? So what does that mean? It means that note that given a grammar, these entries are the same for all inputs and they can be preloaded. So chart 0 is the same for any kind of sentence because I am predicting a .s. Okay, and that could be one of them. Okay, but since I did not read anything, I am predicting any kind of thing that can happen. Potentially there will be more than 1,000 entries in chart 0, depending on the complexity of your grammar. And potentially there will be, at the beginning I am predicting a verb to book. Is it readable? No. Verb to book, noun to flight, etc. So the whole dictionary I am going to put it in there too. So I have to take some shortcuts in this case, but in theory that's the entries of the chart 0. Okay, that's the chart 0. Then what do? I read the first word from my sentence, which is book. Then I see which one of the rules I can progress on. Okay, chart 1. Scanner read the book. So what did I do? I completed this verb book thing, 0, 1, that rule. Also I completed, since verb is completed, VP is completed. Since VP is completed, this verb goes to verb MP rule is progressed. Okay, since verb is progressed, okay, completed, this one is done. Since VP is completed, S is completed. Okay, what else? Since VP is completed, this recursive rule is progressed. Okay, then after that, how about this one? What does it say? Why do I have it now? I added this one new. These are all, see this part? This part is, where does this come from?
From previous states, verb NP, verb PP.
Yeah, since I am predicting an MP, okay, MP pronoun, now I am predicting this, right? Since I am predicting a PP, now I am predicting this, right? So I am adding all of those too. So I modify some of them. This one is completed. Okay, this one is progressed. These are all progressed. Okay, according to your progress, now for the NP and PP, I am adding these rules. Okay, so far what did I do in chart number 1? I have this S. So I am saying that between 0 and 1 there is a sentence, but that's not good. That's not a proper tree. That's not a proper tree because it doesn't cover all the words. So the nice thing would be that's S. I am going to see it at the end of the chart table at the end the C3. So let's continue. How am I going to continue? I am going to read one more word, the. Then in that case, I guess this one will be completed. Completer will move this one first. Then I am going to predict another nominal, right? These will not progress at all and they will stay there. And I guess that will be it, yeah. So chart 2 is here. So determiner that, and that NP is progressed a little bit. And since I have this, I am predicting this nominal, I am going to add these 3. And then when I read flight, this noun is completed. Since noun is completed, nominal is there, and this one will be done, this one will be done, and I will add at the end this one SVP dot. And this is our parsing actually. So it looks like I am not producing any phantom constituents, but I am producing lots of top-down expectations. This is as inefficient as the other one, but still it says that I am going to give you all possible ambiguous parsing of the same sentence. Okay, I can put them in the last one, and you don't have to find the same MP within the same word ranges. I am going to list them one by one for you. Okay. So for such a simple example, there seems lots of useless stuff in there, and that's the stuff. Okay. It is predicting things that aren't consistent with the input. That's the problem with the top-down stuff, right? Bottom-up stuff always produces consistent stuff, but they don't have to come together to produce an S. This one is predicting lots of trees that are not consistent with the input. That's not as efficient as that we like, but we cannot do better than that. Okay. So let's look at this algorithm. The algorithm is here. The earlier parsing says that get the words and grammar I'm going to produce the chart. At the beginning, do this. Just add simple .s rule to the chart 0. Then I will have for loop from 0 to length. Okay, for the chart number 0, for each state in chart I do, if the state is not complete, then get the first word of my input. If it is not part of speech, what does that mean? If it is not part of speech, that means that that's the terminal. Then I am predicting that one, predictor state. Otherwise, move your dot once. Okay. Otherwise, you are done. You have completed this rule. And for this incomplete, for the next cat and predictor and scanner, we have these rules. So it is not that easy to calculate the complexity of this code, a little bit more difficult. But so this predictor is just scanning all the grammar rules for this one. So if I am predicting this P, scan all the grammar rules, okay, that has B on the left, okay. Then if you find it, then I am going to put this one in my chart number J and queue it. The scanner has this one, so it say that if you are scanning for this one, and if you see the word J as part of this one, then I found it, okay, and you are going to add this to the chart number J+1, and the computer is going to do this. If you have this one, alpha dot B beta, and if B is completed, then move this dot from this position to that position. So what? Predictor, scanner, and completer. Okay, predictor is just from that S to this one. I did one. Completer, I just moved this dot from that position to that position. Predictor is, since I have this one PP, I have to edit here. Okay, and the scanner just reads one word from the input. Again, dynamic programming, no repeated stuff in a table, and it can give me all different parse trees for the same sentence. Okay, any questions so far? Second one, top down. First one is more elegant to explain and draw. Second one is kind of, it doesn't work to this, it doesn't work to this. I mean, second one is kind of feels like it is doing exhaustive search, but it is doing it in a smart way. It is not solving the same problem over and over again. So did you solve the ambiguity? The answer is of course not. Of course not. I am going to give you, okay, both C, K, Y, and early will result in multiple S structures for the 0 and entry, okay. They are equally efficient. They work in the polynomial time, okay, and they are obviously using reusing the subparts over and over again. And I'm not going to favor one of them over the other one. Okay, we did not solve the ambiguity. So how do you? Let me go to the table that I showed you here. Not that one, not that one. Remember the green stuff and red stuff. Book the flight through Houston. Okay. How do we solve this ambiguity as humans? When I say book the flight through Houston, which one do you understand? Which one do you think that the intention is?
It depends on the context.
Context, you just look at the context. But without the context, usually we understand that this is the verb phrase and this is the noun phrase, right? The flight through Houston. Why does that happen that way? Because that's the statistics, that's how we use the language. So usually with the statistical parsing, we have probabilities for each rule, and those probabilities are driven from our corpora, from our data set. Okay, that's how we do it. If you don't have the context. Again, this is parsing. We are not talking about how to solve the ambiguity, but the important thing is I left whatever I have as an ambiguous, and I'm not going to address it. Okay. In most cases, humans don't notice incidental ambiguity. Okay. It is resolved on the fly and never noticed. I mean, if I didn't tell you book the flight through Houston that it means two things, we didn't notice it. We take the first meaning, the most common mean, and sometimes when I point to it, you understand that sometimes if the context doesn't fit, then we will go back and we will try to parse it in a different way. Okay. That will be then when I show you this other thing. Remember this one? Yeah. How about this one? San Jose cops kill man with knife. So it is for some reason the man with knife is something that is intended, but it says San Jose cops kill man with knife. I mean, it is man with knife, it is intended, but for some reason cops kill with knife, we understand. That's, I don't know. I mean, scientists count whales from space. What else? Yeah.
If we add the before the man.
Well, why do you think that this slide owner, whoever that was, I think it is Juravsky, yeah, they choose the newspaper headings, because in newspaper headings they don't use the does and a's and etc. Right? They try to write it in a condensed way, and that's what makes it ambiguous for the newspaper headings. Okay. So what else? This one, Dr. No Heart, mutilated body. Okay, so let me, if there are no questions about that, let me talk about this dependency parsing. Okay. Two views of the linguistic structure. One is the constituency. Okay. Words come together and they form constituencies, and we call them noun phrases, verb phrases, etc. And order is important in the structuring of the sentences. That's the one way of looking at this. One way of looking at the sentence structure. Okay. The second one is dependency, and we are going to look at it. So why do we need sentence structure? We need to understand the structure in order to be able to interpret language correctly, understand the structure. And we need to understand what is connected to what. So these context-free grammars are very nice tools to understand the structure, but they are not the only ones. There are many ways to understand the structure. Understand the structure doesn't avoid any ambiguity. Both context-free grammars and the dependency grammars will be in trouble with this kind of stuff, okay? Man with knife or kill with knife, okay? weighs from space or count from space, right? So they will not prevent any of them. PP attachment produces this most of this ambiguity in English. Okay. The board approved its acquisition by Royal Trustco Limited of Toronto for 27 a share at its monthly meeting. Each propositional phrase here can be interpreted as the board approved its acquisition, board acquisition, or something else's acquisition. By Royal Trustco, acquisition by Royal Trustco Limited, or by board, okay? Of Toronto is Royal Trustco or off board, you don't know, right? So each one is causing this ambiguity, and there is a formula, right? Exponentially growing series every time, and I showed you this. I saw the man with a telescope thing, right? If I am connected to the internet, am I connected? Maybe if I do it this way, yeah, it works. I think I will connect.
I saw the man with the telescope on the hill.
I saw a man with a telescope on a hill with somebody, right? So every time you do that, every time you add a propositional phrase, you are adding two more meanings, and the combination will give exponentially different meanings. Okay. I saw a man with a telescope on a hill. What happened? I should not lose this one. So, can I go to, no? I think there is a problem with that thing. Let me go to some other, this one is good, right? But this one. Yeah. No, that's a good idea. While I connect, you sleep a little. Why am I not connected? Yes, I am. Something happening. Okay, good. So, paste it. Images. Okay. I saw a man with a telescope on a hill. Where did it go? It is showing me. Okay, I can show you this one. I saw a man on the hill with a telescope. It can mean any of them, but on a hill with a telescope. I saw the man on the hill with a telescope. Two meanings here and two meanings there. So 2 times 2 is 4. Why there are? So the man on the hill, the man with the telescope. I saw the man on the hill. So I saw the man on the hill with a telescope. Why is there? Anyway, okay. So I think did I show you this one?
Yes.
Okay, we already know that. So each propositional, each PP will give you two new meanings, okay, and you multiply it with each other. So that's gonna give you 4 different meanings. I don't remember why I have 5.
The reason is the possession. The upper case of the
Upper right,
the left
left,
middle, the left middle, bottom.
left, middle. What do you mean? Upper right. This one.
I mean the third one
Second
and the
one.
fifth one. Third one and the fifth one. The meaning, the difference in the meaning is the man on the hill has the telescope or different entities.
The man with the telescope is, both of them are the man with the telescope. Yeah. What? Yeah, the width has 2 different meanings. Okay, with a telescope, that meaning is that owns the telescope or by the telescope. Okay, so with is one, in that one is conjunctive, the other one is possessive or something like that. So it's the ambiguity about with. Okay, so those kind of stuff happens. Yeah, those kind of stuff happens, and we cannot do anything about that. That's the ambiguity. So let's move on. And I am not saying that dependency grammars will solve that ambiguity. They will reflect it. But with the dependency grammars, we don't have to worry about the word order. Okay? So read this sentence in English. So submitted is the head of the sentence. Submitted is the head of the sentence. Subject is bills, right? So bills were submitted by Brownback. Brownback is the name of the guy, okay, who is a senator, Republican of Kansas. Then the bills are about ports and immigration.
On ports and immigration.
Yeah, on ports. So bills on ports and immigration were submitted by Republican Senator Brownback of Kansas. Okay, so this one, I think on purpose did not give us the dependency names, right? This one doesn't say by and etc. etc. etc. Okay. Oh, okay. Good. Now it's here. So subject, object. Okay. Auxiliary is here. This is the modifier. Case, conjunctive, conjunction stuff, and immigration. Okay. So dependency grammar is. Do I have time? Am I going to tell you how the? By the way, dependency grammars are much older than the context-free grammars, and this is a dependency grammar definition of some Persian. Kashmir. Oh, where is this? Where is this from? Can I click on it? Did I click on it?
You did, but it's asking if it should exit.
What?
You did click on it, but it asked if you should exit this site.
Oh, okay. No, I don't want to do that. Click.
Control.
No, can I open it with on a different?
Yeah, use control.
Ya yeni sekmede aç. Anyways, it is very old when it comes. Okay. Doesn't say anything. It's giving me the original thing. Based on the grammar of Panini. So it is very old, and this one is based on not context-free grammars, but the dependency grammars. Okay, and this is how it is done. Just there is a root thing, and root just shows me this completed, okay? The head of the thing is depending on root, and rest of them is marked like this. But I don't have time to tell you how this thing works. Maybe just time for the projectivity, okay? Projectivity is this. Projectivity is this. If you are careful enough, most of the time we can, okay? No two dependency arrows will intersect, okay? No two dependency arrows will intersect. And in fact, if they intersect, context-free grammars will not be powerful enough to explain that grammar, okay? So that's the kind of thing, okay? So no two arrows are intersecting with this case, and most of the time with the projectivity we can achieve that. I think Miramar was a famous code trainer or something, okay? There is no intersection of the words. Let me try to find a case where the projectivity discussion of the outstanding issues was completed. Do you think this is, yeah? I will give a talk tomorrow on Bootstrap. Yeah, there is an intersection here. Give, subject, okay, talk tomorrow. Now talk is, okay, talk is on bootstrapping, but give is tomorrow. So how do I say this to prevent any projectivity? I'll give a talk on bootstrapping tomorrow, right? If I change the order, then it is projective now. Projectivity is not something that we cannot do with the dependency grammars. It is something that you cannot do with the context-free grammars, actually. You cannot, I think you cannot parse this sentence with a context-free grammar, of English. And they say that this is against the rules. This doesn't obey the order of the words and etc. But sometimes they use it this way. Anyway, okay, so I will stop at this point. I'm going to tell you how this dependency grammar parsing works next time. It's not going to be as elegant as the dynamic programming. It's based on machine learning, but I'm going to show you how it works next week. Okay, that's it for today. Start working on your homeworks early, okay?